Hi everyone. Since I can't be there with you next week, I wanted to do a quick exam breakdown. So all the way through questions, we'll break it up into a few different videos. This first video, I'll do questions 1 through 3. So starting here with question 1, pretty much everybody in the class did this correctly. So I'll go through the ones like that very quickly. So the idea is you would have to track across 5 carbons branched to fluorine. So I'm going to kind of pick it at random. I'm going to pick 5 carbons branched and then 1 fluorine, 1 bromine. So my molecule won't be exactly the same as any of yours. Seth's molecule will be maybe this one. So to do that, the key here, and this was the one mistake that some people made on the exam, is that they didn't do this. They didn't do branch. So let's just talk about what an unbranched alkane chain versus a branched alkane chain would be, what the difference is. So an unbranched is a straight chain. So if you had 5 carbons, you would just have 1, 2, 3, 4, 5 carbons. And then, of course, you would fill up so that all carbons have 4 bonds. It's an alkane, so that means all single bonds. But here, if I'm going to do branched, then this is an unbranched. So my branch needs to take one off the end, and instead of putting it on the end, put it somewhere else on the chain. So I could put it like right here, for example, and then I would go ahead and have the extra bonds of the carbon like that. So that would be a branched chain alkane. You could take another one off the end and branch it further. It doesn't really matter from here. So this is the makings of my branched alkane. Then you can go ahead and I would next put on a fluorine and a bromine, and they can go wherever you want. And there was wide variety in the class. So let's say I put a fluorine here and a bromine here, and then you'd fill the rest up with hydrogens. So really the only mistake that people made in the class here really was forgetting to do branched. And I'm actually pretty sure that was just an oversight, that people didn't really notice it. So this would be an acceptable molecule for this first one. And then the next one, you would go through, of course, and list how many elements of each type were in there. And again, I think the only mistakes I saw here were just little typo type mistakes, not where people didn't actually understand things. So of course you knew that it was 5 carbons. So 5 carbons. Then you knew that it was 1 bromine and 1 fluorine, because that's what was defined in your problem above. And the last thing you have to do really is just count the carbons, or sorry, the hydrogens. And they actually should be exactly double the number of carbons. But we can go ahead and count them anyway. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 hydrogens. So that's pretty straightforward. Again, everybody got it right except for, I think, a few just little typo type errors. So on this next one, generally people were able to do this pretty well. You have a lot of options here and you could go a lot of different directions with it. So here's one representation. So this first one, you could have redrawn that. So that's your basic Lewis structure with all the atoms drawn out. You could then do that into a line angle formula or a line drawing, whatever way you want to call that. And so for that, you usually just draw the carbons, 1, 2, 3, 4. That would be your 4 carbons. Then you need to put the branched one off of there. So it goes off the second carbon. And then another bond to a bromine here. Sorry, I made a little mistake there. And then the fluorine again came off of the branched carbon. So I'll go ahead and put the fluorine off of here. Now it doesn't look laid out that exact same way. I could have drawn it flipped over if I had started out with my drawing this way. 1, 2, 3, 4. Then my branch would have gone down, and I could have branched the fluorine off of that and branched the bromine off of that. And that would have looked a little bit more like my molecule, but both of these are they're the same representation of that molecule. So this would be one option. The original one would have been an option. I guess I should have numbered it that way. One option. This would be like a number 2 option. And then most people then chose to next do a condensed structural formula. So for that, you could do that a few different ways. Generally, you would just sort of read down the line here and try to show what's in each location. And you really have condensed structural formulas come in a lot of shapes and sizes. You can actually show some bonds in them if you want to, and that's what I'd probably do here. I'd probably just read down the line, Br, then CH2, then CH, CH2, CH3, because that's the end one, and then the CH actually had a bond to a CH2F. That's probably the best way to do a condensed structural formula, but there are other ways to show that. But this is the one that's most clear. So in this case, I'd really recommend going that way. Again, lots of people did different flavors of the condensed structural formula, and really they were all good. Well, almost all of them. All of them that I can remember were good. So this would have been 3, and this is pretty much the standard 3 that people did. There were some variations on these, like I said. You could then go further to do things like Newman projections, which for that you have a ton of options how you could draw that. You can look down any 2 carbons for this. So for a Newman projection, you might want to sort of label the carbons. So you'd label this maybe carbon number 1 and carbon number 2. So if you remember, in a Newman projection, the front carbon is written as a dot and the back carbon is written as a circle. So the front carbon, carbon number 1, is bonded to a bromine and 2 hydrogens. So it doesn't really matter where you show that. Hydrogen, hydrogen. And again, it really doesn't matter where you show this because these are all single bonds, so they can all rotate into different shapes, which is actually going to be relevant in the next video. So you can show it in any rotational form you want. Those aren't different isomers. They're just the same molecule flopping around. Just like you can move your arm up or move your arm down, but that doesn't make you a different person. Same thing. These bonds can rotate. They're not a different molecule. They're just flopping around as it can do. So then that's the first carbon that we drew. So we've only drawn that. And then the second carbon, we have to make sure we get everything bonded to the second carbon. Okay, so what's bonded to that second carbon is a hydrogen, the CH, another CH2, CH3, coming off that way, and then a CH2F. And that's it. That's a good Newman structure for this, or Newman projection. You can also do a Fisher projection. Someone did that one and did a great job. We haven't actually studied that yet, but it was spot on. It's perfect. They're pretty easy to do as well, but we'll study that a little later. So that's it. That's a number you could have done. Like I said, there are different flavors of these, but this is the basic things that we would have learned so far. Oh, I'm sorry. There's one more that no one did that you could have done. I remembered that it would have been great if someone had done this, and it's kind of a variation between this and that's showing the 3-dimensional shape. So you would have drawn your carbons in the row like that, your 4 carbons, and you would have drawn your branching like with the wedge and the dash. So all of your carbons would have gotten their wedge and their dash to show the 3-dimensional shape. So then this one would be branching off to another carbon up here, and you could have shown it. You could have shown that in 3 dimensions as well, but you can still just say CH2F up there and then H. This would be the standard way to do it. This one going to the bromine, these ones going to hydrogens, 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 hydrogens. So that's actually a 5th way that you could have done it that I didn't actually list, so no one thought to do it, but that would have been an excellent way to do it as well. And again, there are a few different variations of that. You could have tried to draw 3 dimensions around that carbon for sure. But usually we just draw a 3-dimensional shape around the main chain when we draw these. All right, so that is it now. That's 5 ways you could have done it so far in the class that you've seen. And you only had to pick 3 of those. So thanks for hanging with me. Next, we'll start talking about polarity of this molecule.